Start video. I'm going to be showing you how I make for the maze algorithm. I'll start by briefly explaining the 2D normal algorithm, then the Wilson algorithm, then how everything scales up to the extra dimensions. To start, this section of code initializes a bunch of variables and lists I will be using later. Vertical and horizontal walls, simply the walls in the maze, and visited cells to keep track of the cells that have been visited. This algorithm, the depth-first search algorithm, requires keeping track of all the moves that have been done. So this previous moves array works, and this temp variable simply counts up the number of visited cells, and when it is equal to the size of the maze, we know we are done. To start here, the algorithm checks to see what moves are valid. This checks to see if it's on the bottom of the maze. If so, it cannot move down. And this checks to see if the cell below it is empty. If it's not empty, then it can't move down as well. If not, it's allowed to move, which sets available moves 0 to true because 0 up, 1 right, 2 down, 3 left. I use a different method for higher dimensions. I just chose this one randomly, and I regretted it. Next, we check to see if it's equal to an empty Boolean array, which means that there would be no available moves. If there's no available moves, this algorithm takes a step backward. So it checks what the previous move was, does the opposite of that, and then steps back in the index. And we'll keep doing that until it finds a valid move or the maze is filled. If not, there is a valid move. We make a new array list, fill it up with all of the items, and then choose a random move from that list. Based on that random move, we will remove one of the walls in the way, as well as moving our own location based on the move, and then setting the new cell to visited, and increasing the variable by true, increasing the index by 1, and recording the move. Once that is done, the maze has been generated, and we call a draw maze function. Main here. Taking a while. What? Okay, I don't know what happened there. Oh, that's my bad. This is a small example of the maze. The drawing of the maze starts with this, which simply prints out the top of the maze, ignoring everything else. This thing then loops through essentially pairs of points, so that would be a vertical section, then a horizontal section. It does that once, twice. As you can see, there's the vertical section, here's the horizontal section, before it prints out one more vertical section for here, and finally the base of the maze. Of course, checking to see which walls do and do not exist, as whether they should print out the vertical lines or nothing, to see if you can get through them at all. As a slightly better example, I will be making a larger maze. Here it is. You may notice that this algorithm is very biased towards extremely long and uninteresting corridors. It's fine, but that's the main reason I'm switching to the reason I spent a bunch of time making this algorithm, the Wilson algorithm. Its main benefit is that it has an even distribution between all mazes, meaning while the depth-first search algorithm is biased towards long hallways, this one has no bias whatsoever. Here we initialize a bunch of variables. Visited line cells and visited line moves are notably different, but they are similar to the previous move index, except we need both of them. I changed over to X and Z walls instead of vertical and horizontal because it was clearer. This is similar for initializing variables. Visited cells, this algorithm starts by setting one random cell to visited. And then, same thing, we wait until the variable is equal to the size of the maze, index. So this algorithm makes one point valid, selects another point randomly, and then starts walking around randomly from that second point until it reaches a valid cell, at which point it cuts out all potential loops that it had, and takes the not shortest path between them, but one without any obvious backtracking, removes all the walls in its way, and sets all those cells to valid and starts again. So this is the initial valid cell. This thing sets index X and Z as the cell that it is starting the walk from. We have this random walk function. All it does is messes with these two arrays. Random walk, if I go down here. It starts by making a duplicated cells list, which is how it checks if it backtracks on itself. It starts by going down here, selecting a move at random. Of course, it cannot walk into the bottom or top of the maze. So this is the same available move thing. This is a slightly different algorithm to select something from the available moves. This one only changes the position, doesn't switch out any of the cells because they might be removed later. We record the moves here, and then find items. This is a function that I made a while ago that creatively named finds items. So this index X plus index Z times 20 is essentially just a way to transform the pair of coordinates into a single number. So since visited line cells has this item in it once at a minimum because that is the final item and is looking for it, if duplicate cells is equal to 1, that means that there is only the one copy and the line has never gone there before. If not, there is a self-intersection. We check here to find out how many cells need to be removed. Each cell is removed, as well as the index is decreased for both the moves and visited cells. And finally, if we have made it to a valid location, just return. After doing that, we have to get the actual visited cells index and each of the walls to agree with the path that we just walked. So since we are aware that it is already a valid path, we don't check for anything, simply setting the walls in the way to false and moving before setting the cells to visited and increasing the temp variable. We do overcount by 1, so 1 is just removed at the end. Once this is over, meaning we have connected every cell to the maze, we get to the draw maze function, which I managed to just directly copy from the previous 2D maze drawer, because that was one of the hardest things to do. Here's an example. It looks very similar at small sizes, but at larger sizes you can see that the number of just single long corridors is much less, so it is still solvable from bottom left to top right. And for the 4D maze, I'm skipping over the 3D because it's less interesting. It was honestly very similar to Make, but displaying it was the problem. It starts by initializing all the variables. This is more complicated, but the integer function is large enough to just hold everything to its maximum value. Same thing here, everything generated, initialized to true, random cell visited, random cell selected, random walk, exact same thing, but with extra steps. The walk is, once selected and redundancies are removed, it is checked. It's just for testing. And draw maze. So draw maze is definitely more complicated. I'm going to start by bringing up a random maze. So this is a 4-dimensional maze. It is a 2D grid of 2D mazes. So if you start here, the R represents right, meaning you go to the same cell, but 1 block over. Of course, there is the corresponding L, meaning you can go back. There's R, U, D, and L, as well as if the wall is missing, you can simply go between them. Yeah, this will take a while to solve, and I don't feel like doing that. So the W-axis is the large one, meaning going left and right between the entire cells. The X-axis is within one cell. The Y-axis is between cells going vertically, and the Z-axis is between cells within them. So just within cells. I know that is not the best way to do it. It is the only way it was the easiest way I could remember how everything works. So draw maze is called a bunch of times, where this I represents its Y value, meaning it will call once to draw this, call once to draw this, call once to draw this. So here's the thing, it starts by drawing out the very top, then cycles over Z, meaning it goes small, then W, so large, then X, then Y. Oh, wait, sorry, it's Y, then Z, then W, then X, meaning it does the proper order to just draw everything out, eventually. It is fairly similar, except with another loop, or another 2 loops, the W and X axis, requiring more mazes to be drawn. An additional thing is this draw maze data function. It's just what is in charge of the U, D, L, and R's that are within the cells. And that means I can make something absolutely unsolvable like this if I so wish. Although the computer doesn't often like displaying it. There we go. I assure you this is technically solvable, but it is not by humans in any reasonable amount of time. Alright, that is my algorithm. I hope the coughing wasn't too terrible. Bye.